Welcome everybody, my name is Dirk, this is Péter, and today we'll be presenting our SoK on neural network extraction through physical side channels. So let's start with neural networks themselves. So neural networks have been around for ages now. They have applications in autonomous driving, in medical imaging, and of course one of the most famous ones is image classification. So when we take an image of an extraordinarily cute dog, we put it in a network and then it will be classified as a dog, which is all correct. Now there are four components here. Let's start with the input. Then we have the architecture, the parameters, and the output. Now where there is something interesting, an interesting piece of technology, there are also attacks, and we will consider model stealing. So model stealing is when an attacker, well, as the title says, steals the exact same model. So what happens is, well, we have our model and it's classified as a dog, and one incentive could be, well, consider that the user pays the network some amount of money to classify, to do the job. Now, if the attacker stole the model, he could gain a monetary advantage, which is one of the incentives for model stealing. Now, model stealing can be done in several ways, and we will talk about, of course, the side channel approach. So again, just a brief recap, the side channel we consider a chip, a scope. We connect it to each other or with an antenna, and then whenever some piece of data is being processed, power is being consumed, and with that we can capture traces which will reveal some information about what is being processed. The rest of this presentation we will first talk about neural network extraction, and then of course the systemization that we performed. Then architecture extraction and its limitations, parameter extraction and the sensitivity of it, and then input recovery and a new approach, after which we finish with an outlook on neural network extraction. So neural network extraction and how we grouped this. Again, we consider the same network and there are four components. Now we systemized all the work that considered physical side channels to steal a model on input, architecture, and the parameters. Of course, these are all the papers. It's not intended for you to read them. It's unreadable. We classified them on their platform, the model type, and the attack path. And you can read this in our paper. Right, so let's start with architecture extraction. First, the framework. So what happens is you have the patterns and power traces. You do some simple power analysis, and then one of the methods is to use common patterns to determine the hyperparameters that eventually determine the architecture. Now, simple power analysis works as follows. Over some experience, you saw two patterns for different networks, and then upon receiving a trace like this, you'll quickly see, okay, this belongs to, let's say, network X. All right. Now then, what happens with common patterns? Common patterns can be anything that is occurring quite often or not at all in real-world scenarios. Take, for instance, the ResNet50 architecture. And we see here that there is one activation function, ReLU, and one interesting fact is that there will never be two activation functions subsequently placed, meaning that that is one pattern that you can use to determine some part of the architecture. All right. Then the second method to determine the architecture is hyperparameter optimization. Basically, you use simple power analysis to determine the architecture, then start with some parameters you either get from an online model or some default values and optimize that until you get a correct architecture. And then hyperparameter derivation, and one quick incentive is to, when you look at this simple network, when we have two layers and the first layer has 4 output channels, the second layer must have 4 input channels, otherwise the network does not match. And of course, there are more equations, and again, you can read all about it in our paper. All right, and then the limitations. So All these architecture extraction methods have some assumptions. For instance, that only 4 activation functions are used, that only limited layer types are considered. The stride is either 1 or 2, and the kernel is always a square. And this limits the scope of the attack. Now, and that's not always necessary to do. For instance, consider that the kernel is not a square, but in this case, well, a 1x4 vector instead of a 2x2 kernel. At first glance, the traces look the same, but if you properly align them, you will see that there is in fact some timing difference, which can be used to distinguish the two. Now, of course, this is a very bold example, but what if the kernels look alike? So we have 3x4, for instance, and 4x3. And also this has the same number of multiplications being executed. You still see that there is some sort of difference, which can be used to, well, increase the scope of architecture extraction. And therefore, the assumptions on architecture extraction can be relaxed.
All right. Yeah. Now, next we have parameter extraction. So parameter extraction naturally comes after architecture extraction because you need to know the architecture in order to be able to extract the parameters. Now that you have the architecture, the hyperparameters, now you have 2 main methods to extract parameters. One of them is differential power analysis in the literature, which has been used. And in this context, DPA targets intermediate results in the network, in the layer, in a divide and conquer approach. So it goes weight by weight in every layer. And this is how DPA works to reduce complexity in neural networks. There are also techniques that exploit non-constant timeness of either activation functions or floating point computations to extract parameters. Regarding some of the challenges, so as opposed to cryptographic attacks, parameter extraction can be very expensive because in practice, models, their size range from millions to billions of parameters, and we yet to see attacks that can actually pull this off. So it's very costly. However, the attack is highly parallelizable. In addition, some attacks rely on chosen inputs, which of course assumes a stronger adversary. So if you don't get to choose the inputs, some of these attacks may not work. And also it hasn't been addressed whether if you incorrectly recover weights, just small errors, how they affect the recovery and the accuracy of the recovered model. So we designed an experiment where we took off-the-shelf well-known architectures and simulated how errors propagate in the layers, in the weights, if you recover the weights incorrectly. And for example, ResNet, the larger ResNet is more robust to these kind of errors than the smaller ones. In addition, if we compare it to other architectures, mobile nets are very sensitive to errors in the recovered weights. Oh, holy shit. Yeah, so next we have input recovery. For the inputs, in theory, you can use the same techniques as for parameter extraction. However, for inputs, the adversary is usually limited to single measurement, so they have only one shot. So techniques like DPA are usually limited to a horizontal attack, which in some cases may or may not work. In addition, there are other approaches which sort of aim to reconstruct a silhouette of, let's say, an input image or just partial information based on setting thresholds and deciding whether this is a black pixel or white pixel. So as I mentioned, this one-shot scenario really limits the adversaries in what they can recover regarding inputs. And attacks like DPA require knowing the architecture and the parameters of the target model to mount the attack. And we have exclusively only seen grayscale images targeted in the literature. But some approaches have done full input reconstruction may not be necessary. So we designed an experiment, an attribute extraction experiment. So let's take our previous example of a network classifying a dog. And if we measure the power trace during this inference, you can also see that this image has other objects, like a computer in the background, and we can train another classifier to detect these objects. So for example, we measure the power trace, and given the power trace, we can classify that there is indeed a computer in the image. So our conclusion is that partial reconstruction may already be enough in the case of input recovery. So as a small summary, for architecture extraction, the literature is very limited in the search space that they explore, but they can extend their work because, as we show, you can extract fine-grained details as well. Although we yet to see countermeasures against architecture extraction, although there have been some constant time implementations for activation functions, which may count as a countermeasure. For parameter extraction, it can be an expensive attack. The larger the model, the more expensive it is, and the more time it takes. And as we've shown in our experiment, the accuracy of the EPA has to remain high in order to get a functional model. For input recovery, it's really the one-shot scenario that very limits the attackers and the information that one get out. So as a takeaway for future work, architecture extraction methods could explore more fine-grained details in what they want to recover with respect to our hyperparameters. And as we've seen, parameter extraction is dependent on the model size, and the larger the model, the more expensive it is in terms of computing resources and time. And input recovery could do with other avenues explored as well. And that's it. We are happy to take your questions.